Okay, so welcome back. Now we're ready to do an empirical application after this simulation exercise. And we're going to talk about the effects of married women's labor force participation. The example I kind of introduced in the very first video on panel data models for binary responses. Okay, so let's just read in the data and create some variables. Okay, so you've seen some of the data set before. We had, kids and education and a bunch of other variables. And then we have as a dependent variable, the labor force participation of females. Okay, I'm going to add here a bunch, create a bunch of regressors the lag dependent variable, and also this is the initial condition, the first observation. So here I call one, that's period one, because that's the first period in this data set. So this is why I see 0 in some sense. And then I create some averages or time series averages for some of this the explanatory variables. Okay, so this should be done now. I think what we could do is look at this data set, and now we have like all these different variables. This is I kind of transposed it and looked at only the first individual, which is like the first five observations. So here's like a list of all the different variables that you see in the data set. You got your ID, your period, and the labor force participation, which is, sometimes it's 0, sometimes it's 1. You got you got these demographic variables and education experience, and then you got an indicator for kids. This is like this is one of our sets. Okay, and then you got some time dummies, and what I've done here is then I've computed time series averages for children. So this is a person who has children in all periods, so that average is 1. But then we also have the individual specific average of the log of the husband's income. So you see it's constant over time. But with original variable, that's time varying, definitely log of it's right here. You see it's varying over time, but then this is approximately the average of those variables. That is the actual average of those variables. And then I'm also creating another set of variables. This is the number of children in period 1, in period 2, in period 3, in period 4. So you kind of have those variables in all time periods in case you want to have that. Okay, so you can actually control not only for, say, the average, if you want to do correlated random effects, average of all those explanatory variables, you could have them in every time period. You completely, control for it. If your interest is really in the lag dependent variable, well, that's a way to move forward. If your interest is in that coefficient on kids, well, of course you cannot do that because then you lose identification. And then you do the same thing with log household income. Here you see or log of husband's income. You see here, this is the income in the first period corresponding to that number here. Okay, and then you got the lag dependent variable, which is not observed in the first period, right? Because we have only had 5 periods of data, so we're going to have to delete that period when we're doing our dynamic models. Okay, so we lose 1 period of observation once we do dynamic modeling. And then we have basically the initial condition here, the really repeated across all time periods. Okay, so this is how our data looks, and we're going to use this for estimation. Okay, so here what I'm trying to do is I'm replicating the results from the columns 1 to 4 in table 15.3 in Woolrich. So you can look at up in the book. It's on page 623. And see if things add up. Okay, so the first thing we do here is we're going to estimate a linear probability model. Okay, linear probability model with fixed effects. Okay, and now we start in the world of static models, so no lag dependent variable, and this would be fine, right? So here's a coefficient on, let's just focus on the one on kids. It's minus 0.9. Okay. Now, if we move on, it's do a pull probit. That's the next column. This is, we could also, we kind of did that. We could also do the pooled OLS, right? then we'll just write pool OS here, polls, and then we get a fairly smaller number. Okay, but let's just stick with this one. Um, okay, so this is trying to control for this on unobserved effects, and also for any correlation between kids and those and any of these experimental variables and then the unobserved effect. It's a fixed effects model. So the pull pro bit, well, here the partial effects are numerically twice as large compared to what we got over here. Okay, so these are not identical. Okay, these are not identical. So this is kind of suggesting that there may be actually some correlation between the explanatory variables and the unobserved effect. So we may want to actually try to see if we can control for that in this correlated random effects way, okay? By including, say, averages. This is what we call the X bars, okay? Including basically the individual specific averages of our explanatory variables. So we have kids and log of husband income, but we also have the averages of those. And you can see they're actually quite significant, especially the coefficient on income, suggesting that there is some correlation between the explanatory variables and that unobserved effect, okay? Or at least the error term. I mean, here we're estimating a pool pro bit, so we are not really, modeling the persistence in the error term. That would require like a random effects pro bit. Okay, so again, now that coefficient on the average partial effect, well, that's actually very close to what we found with the linear fixed effects regression. So it seems like including those averages of the explanatory variables, these kits bar here is actually controlling kind of nicely, and it's taking down that's larger average partial effect we had without them here in the direction of that average partial effect we estimated with the linear fixed effects model. So these things are kind of adding up. Okay, now we're still in a world of static models. Let's do the correlated random effects model with the controlling also, again, controlling for time, individual specific averages of over time for kids on log of husband income, but then also estimate the coefficient on the unobserved effects variance, okay, or the standard deviation here is not squared. And now here it's 4. And for the reader of Woolrich's textbook will find in the table that everything else actually adds up in terms of the average partial effects, and that actually it's very close to the average partial effect, very close to what we found for pool pro bit if you compare. But that coefficient here, that coefficient is different from what is in column 4. And the likelihood of my equation here is higher. So I have a higher likelihood compared to what is in the book. And so what is going on? I was not fully able to do that. I mean, in order to actually compare the numbers, you have to compute the, he's not really showing this number. He's showing 1 divided by 1 plus this squared, the square root of that. Okay, and so even if you compare those numbers, you find out that this coefficient is much higher in our case. Okay, and then I was trying to run this, actually replicate his results using Stata, and see could I actually replicate what he had in the book, and I could replicate everything, but then then if I was doing that, running the same regressions here in Stata, and by the way, this code is also available in the repository, then I was not getting the same. Okay, and I suspect, and I've seen actually a print of the exact same numbers in Woolrich slides, where he's running that command on that same data set, and is getting another set of coefficients. And I think that may be actually a bug in Stata in the previous version in 2010 that was not appropriately accounting for that unobserved effect. Anyway, so I have estimating, so I trust this, actually trust this more than what is in the book. But anyway, this is if you can find the bug, let me know. I'm pretty reassured by the fact that these coefficients here are well, maybe actually, yeah, no. So these coefficients that we're estimating here, they are we tried it out of the simulated data and they really add up. And the only difference I can think of is that I'm making I'm doing for the random correlated random effects, I'm doing Gauss-Legendre, but I'm using quite a lot of quadrature points. And it's stated that we use Gauss-Hermite, so maybe that's a little bit more precise. But then I don't think so actually. In any case, I get a higher likelihood. Anyway, so let's move on to the dynamic models. And these are selected results from example 15.6, and there's some nice text in the book around it. I just want to end up with some estimates here for the pull probit first. Okay, so first we'll just do a pull probit for the dynamic model. And now the new thing we've added here is the lag-dependent variable. It's a coefficient on that is highly significant and positive, and average partial effect of 0.35%. Okay. Of course, this is not the way you would calculate the average partial effect. It's a binary variable, so you would need to essentially calculate the probabilities when y is equal to 0 and the probabilities when y is equal to 1, and then subtract them from each other, and that's your average partial effect. Okay, it doesn't really make sense. I mean, these are calculated as average partial effects, assuming that we're making like a marginal change, which doesn't make a lot of sense when we are talking about when you're talking about a binary variable. Okay. Anyway, so but I'm going to compute that in a second. Okay. If you do the pull probit with controls for the potential correlation with the explanatory variables, here I did not only include the averages, I include basically indicators for how many kids you had in period 2, 3, 4, and 5, and basically also what was the income of the husband in log household log income of the husband in period 2, 3, and 4, to control for any potential correlation between those explanatory variables and the unobserved effect. Okay, at any time. Okay. Along with the time dominance and the other variables, and then the main interest here is on this coefficient. Okay, the average partial effect is 0.27. Okay, so it falls a little bit, but we have not appropriately controlled for any unobserved heterogeneity because it's not a random effects dynamic probit model. So we know that this could be really due to spurious state dependence. So let's look at the result if you control for that. We find quite large, quite significant amount of unobserved heterogeneity. The variance is 1, but it did drop quite a lot. It was 4 before, and now it's 1. Okay, and this is essentially because we have a dynamic model. So now we're really taking a lot of the persistence out and trying to separate these two effects. Okay, so you can say that variance before was large because it didn't account for the true state dependence, and you can say that these estimates you got here a too large effect here because you're not accounting for the unobserved heterogeneity. So we want to separate these two effects. Here the average partial effect is 0.15, and again this is for a continuous change in a binary variable. Doesn't make a lot of sense. So let's actually compare the first specification with the second specification in the correct way. Okay, so so here the state dependence, if you look at a discrete change in x in the lag dependent variable from 0 to 1, is around 0.25. Okay, Now, if you take the numbers from the dynamic pool probit, that is not correct for the unobserved heterogeneity and all those additional controls for initial conditions and so on, it is 83%. That's a lot. Okay, that's a huge number. So think about what is the policy implications of this number. It means that you got some married women, you want to get them into the labor market. What you do is you put them into the labor market in some job training program, or whatever it takes, just put them into the labor market. Then they're going to increase the probability of participating in the labor market next period by 83%. That's really bang for the buck if you're making policy. Okay. Whereas if you're estimating the true effect, it's much smaller. Okay, it's much smaller. Of course, I mean these yeah. I mean, already this is already a pretty big effect, and maybe there's things we are still not capturing. Okay, that give rise to spurious state dependence, but it's definitely much smaller. Okay. Anyway, so this is a way, and you can sit down and actually see how did I calculate this for average partial effect. It's essentially I first here what we do is we take the sigma hat we estimated from the random effects probit. We then scale all the parameters with that. Remember, because when I'm calculating the probabilities, I'm not integrating over that, so I'm just dividing all the coefficients with one with the square root of 1 plus that sigma a hat squared. Okay, to get the beta divided by sigma. That's what entered into that partial effect. Okay, when you're integrating over the unobserved heterogeneity. And then essentially what I'm doing is I'm taking out the betas, I'm taking out the rows from the parameter vector. Then I'm creating a new parameter vector that where I put that row parameter to 0. Then I calculate basically what is the probability for being in the labor market in that particular case. And then I take the probability in the counterfactual where I add the row parameter, because that's like, now y is equal to 1 in this case, and here up here y is equal to 0. So you got basically two different probabilities. You can calculate the partial effects by subtracting them from each other. And actually, these are average partial effects where you have averaged out the distribution for C because we have scaled all the coefficients. And then I here average overall, so the distribution of the exponential variables to just get one number. And this is both across individuals, across time. Okay. And then I do the same thing here for the pool probit, except that I'm not scaling in a coefficient, and this is how we got these results. Okay, some remarks here on the, oh, I feel like there's something missing here. I think maybe we should open up here. I think there's something here is not here. I wanted to show you like a histogram of those partial effects, but they're no longer here. Well, you can do that histogram, but try to make a histogram of these average partial effects from that random effects probit, and you will see you get something that's very different. Okay, so anyway, so let's back to the conclusion here. So some remarks in this empirical example. The linear probability fixed effects gives actually a pretty good approximation of the average partial effects in the static models, but it fails. So I didn't even try it. So in the dynamic models, the pool probit gives much higher estimates, indicating the kits and the log of household incomes are correlated with the unobserved heterogeneity. This is what we saw when we compared, pool probit with the linear fixed effects model in linear fixed effects in the static models. The random effects with controls for means of kits and log household income get very similar effects, kind of indicating that we are successful in controlling for that correlation between the exponential variables and the unobserved effects. And then in the dynamic model, pool probit results in spurious state dependence, because we're not accounting for that unobserved heterogeneity, which is, and these results are much higher than the result from the correlated random effects model, where we had like 0.25 or 25% increase if you are if you go from 0 to 1, if you are already in the labor market compared to if you go into the labor market. So that's kind of it. So let's just stop here. Okay.